In this example, we're being asked to replace this circuit with its Thevenin equivalent. And of course, the Thevenin equivalent is simply a voltage source, which is Thevenin, which we should find, in series with an Thevenin, which we'll also find. Okay, so let's start by the Thevenin. So the very first step to finding Thevenin is finding the open circuit. So we're going to take a look at AB and we're going to keep it open circuit. We're going to open circuit it basically. And we will say, well, the voltage we're interested in, this here, plus minus, this is the V open circuit. And we use circuit analysis technique. And in this particular case, I identified that there's an essential node in here, there's an essential node in here, there's an essential node in here. If I pick this to be my reference, this will be definitely 30 volts because it's above the 30 volt source, and of course all of this is the same. All right, so and this one here will happen to be my V open circuit. So this is the actual open circuit voltage that I'm interested in. So all I have to do is just write one nodal analysis equation, and I'll be able to figure out what V open circuit is. So V open circuit here minus 30 divided by 15 kilo ohms, so that's in milliamp, plus 3 milliamp, which is good, plus VOC divided by 5 kilo ohm, and that should be equal to 0. And that should give me the answer of what V open circuit is, and that number will be negative 3.75 volts. So I have just identified that this particular number here happened to be negative 3.75 volts. By negative meaning, usually Thevenin is the positive is on the top and the negative at the bottom. By negative meaning, my assumption is just wrong. It's actually the opposite. But anyway, regardless, we just keep it this way and we continue. So that's V open circuit. So we're done with step one. So the second step is to figure out what the Thevenin is, and there are different methods to do that. So I'll show you which method apply in this particular case. So let's double check here. So method one, what does method one tell me? Well, method one tells me, let's take a look at this circuit, turn off all the independent sources and find the R equivalent. And as it turns out that all of these are independent sources, so I will be able to use method one, no problem. And frankly speaking, that's the simplest method for this particular problem. Okay, so we have the 10 kilo ohm, and of course, turning off the current source is just basically just open circuit it. And then we have the 30 volts we have the 30 volts, but before we do, the 30 volts gets replaced with a wire, and then we have the 15 kilo ohms in here, and then the current source basically is open circuited, and then what we have is a 5 kilo ohm in here, so that's the 5 kilo ohms. All right, and that here is A, and this one here is B. And now what we're interested in is figuring out the R equivalent from here. And the R equivalent will be my R Thevenin, okay? And of course, if you take a look at here, this wire, because it's in parallel, this wire here is in parallel with this resistor. So this resistor doesn't exist, it's shorted out. So that leaves me the 15 and the 5. And the 15 and the 5, they have this node shared and this node shared. Remember, it's like this one here and this one here. So they are in parallel. So the R Thevenin or R equivalent will be equal to R Thevenin, which is just simply 5 in parallel with a 15, and that value should be equal to 3.75 kilo ohms. Okay, so that here is 3.75 kilo ohms. All right, so while we're technically done, I was able to find the Thevenin equivalent circuit for this one. I want to show you how we can apply method 2 and method 3 to find the R Thevenin. So let me just show you the second method. Okay, so here's method 2 to finding R Thevenin. So method 2 tells me, well, what you need to do is you need to take the original circuit, the one that you have in here, and let's do a short circuit on it. So let me just copy this here, and that's what we do. What we do is we short circuit it. So here's that. So we're going to take that circuit in here, we're going to copy it, and we'll short circuit it. So let me just do that here. All right. So we do this here, and what it tells me is, okay, let's do the following. You take this wire in here and you short circuit it. So all you have to do is just basically here, and you compute what the I short circuit is. By figuring out the I short circuit, I'll be able to compute what the R Thevenin is. Okay, so what do we do in here? Well, first, this is the I short circuit, and because I have I short circuit, so technically this resistor doesn't exist. Okay, so I'll basically just remove that. So this one here is shorted out. Okay, let me just do this. All right, then while I short circuit is simply the I, this is, let me call this I15, and of course that will be 13. So if I write KCL in here, okay, I don't think I need to do any analysis because I have pretty much everything I need. Okay, so this node in here, I will tell you, well, I 15 equals 3 plus I short circuit. Basically, this is just simple KCL in here. Let me just make sure I write it. This is KCL at this particular node. The current going in equals the sum of the current going out. What I'm interested in is I short circuit, and that should be I15 minus 3, and those are all in milliamp. But what is I15? Well, I15 is the current across that 15 kilo ohms. Okay, do I know the voltage across the 15 kilo ohms? Well, if I put a reference node in here, that voltage here will be 30 volts. What about this voltage in here? Well, it is the same point in here. This is also the reference. There's no difference because of this wire. So this happened to be 0 volt. So frankly speaking, yes, I do know what the I15 is. And that I15 is just simply 30 volts divided by 15 kilo ohm. Okay, minus 3, that will be the I short circuit, and that will become basically 13 divided by 5 is 2, minus 3, that's negative 1 milliamp. Alright, so we know the I short circuit, so that tells me the R Thevenin is simply V open circuit divided by I short circuit. Okay, and what is the V open circuit? Well, we found out the V open circuit a few seconds ago, and that is negative 3.75, so we'll just use that. Negative 3.75 divided by negative 1, and that will be 3.75 kilo ohms. And that's exactly the same value we found a few seconds ago by doing that method 1. All right, so method 1 and method 2 basically agree. All right, what about method 3? So here's method 3, okay? So method 3 tells me, well, you have to turn off sources, all the independent sources, keep the dependent source, and connect an external source, basically a test source. So we can replace that current source with basically an open circuit. We just basically remove it. Do we have another current source? I think we do. So we're going to remove this one here as well, because this is how we replace it. And the 30 volts become a wire in here. So let me just do this here and just replace it. So we replace this here with a wire. All right, so now what are we interested in? Well, we're interested in connecting some sort of a test source in here, and we can compute a voltage source or a current source. It's up to you. I will choose to be, maybe let's do an I of t, for example, and I'll set that to be 1 milliamp. Okay, and my task now is to figure out what the V of t is here. Okay, so let's take a look. Frankly speaking, this particular resistor is in parallel with the wire, so it doesn't exist, it's shorted out. So that leaves me that 15 and the 5 share this node, and they share this node, so they are in parallel. I can basically combine them. So if I combine them, I'll end up with 15 in parallel with the 5 kilo ohms. Okay, and that will be in, well, it's a single loop circuit in here, and that I know that that's I of t, and I set it to be 1 milliamp. And what I'm interested in is the V of t across it. Well, V of t is just simply I of t, which is 1 milliamp times 5 in parallel with the 15, and that will be 3.75 volts. All right, so that tells me, well, the R of Thevenin is just simply V of test divided by I of test, and that will be 3.75 volts divided by 1 milliamp, and that's 3.75 kilo ohms, and that's exactly the same number that we've seen before. So the Thevenin equivalent for this circuit is just a voltage source, and that voltage source happened to be negative 3.75 volts in series with R Thevenin, and the R Thevenin happened to be 3.75 kilo ohms. Okay, and you can do a source transformation to figure out the Norton equivalent as well.